Hi everyone, I'm Professor E from Neutral Plastics, and today I'll be running through our proposal for you, Bentham Corp. The process for the production of VCM utilizes ethylene, chlorine, and oxygen feeds, which are passed through multiple major units with varying conditions. To make it more comprehensive, we will be analyzing the proposed process with an extensive review on the model selection processes and followed by the energy analysis. Let us first have a look at the PFD. To simplify this, we will be splitting it into 5 main stages. The first 2 stages consist of 2 separate routes which produce the intermediate product EDC. In the first route, the direct chlorination unit, ethylene and chlorine are catalytically reacted in a bubble column whose conditions prevent the formation of beta-trichloroethane. On the other hand, the second route, oxychlorination, uses raw ethylene, oxygen and recycled HCl from downstream carried out in a fluidized bed reactor. The reasoning for this will be later explained in stage 4, so stay focused. This EDC is then purified here in stage 3. This stage consists of various separating units, with the EDC firstly being passed through 2 flash drums separating residual, reactants, side products and impurities, followed by a scrubber which neutralizes the highly corrosive HCl. The EDC is then sent to a decanter which removes water and finally sent through distillation columns, which remove unwanted byproducts and any remaining water. These units all operate at the following conditions. This stage is crucial to optimize the design, as an EDC feed with high purity increases the VCM yield. In stage 4, the purified EDC is then converted to VCM inside this furnace. Through these extreme conditions, the EDC is thermally cracked to VCM and HCl. Now, remember the reference I made when we were in stage 2? Well, this is the reason why we have suggested to include an oxychlorinator in the process, as we could recycle this toxic byproduct to produce more EDC, thus increasing the product yield, benefiting Bentham Corp both economically and environmentally. Finally, in stage 5, the VCM is purified to meet the required specifications. The first column removes the HCl, recycling it back to stage 2, as mentioned previously, while the second column removes the unreacted EDC and recycles it back to the furnace at these conditions. And that's the whole process. This process produces VCM which meets the desired design specifications. The proposed route was then simulated to verify its feasibility. Before the Aspen simulation though, we had to determine the suitable thermodynamic and Aspen models. For the Aspen reactor model, R stoic was chosen as there was substantial data on the conversion and selectivity relative to R yield, which had inconsistency in their literature yield values. On the other hand, with choosing the thermodynamic model, 3 major factors were considered. Different models can result in differences up to 293% between the calculated process flow rates. 3 models were originally selected. Hey! Anyways, based on literatures, NRTL was chosen as the plant-wide base model, as it has already been successfully used to model VCM plant previously. However, it is important to note that NRTL has a significant drawback, which is the inaccuracy of high-pressure systems. Knowing this, when analyzing our PFD earlier, we noticed that some of the units in the process operate at very high pressures, such as the furnace in stage 4 and the last 2 distillation columns. Hence, for these units, the SRK thermodynamic model was used instead, which uses an equation of state to correctly predict the behavior of multi-component systems at high pressures. Our design was then further optimized through energy analysis, which identifies methods to reduce energy expenses through heat integration. It was found that the main areas of heat generation were the condensers of the distillation columns and the direct and oxychlorination reactors due to the exothermic reactions. Conversely, the areas of high heat consumption were the reboilers of the distillation columns and the EDC furnace. Firstly, a pinch analysis was carried out in order to match heating requirements between the streams, resulting in a reduction of 42.9 megawatts from what was originally found to be 77.1 megawatts. The possibility of integrating the reactors with the streams as well as the distillation columns with one another was also investigated. However, the safety issues and infeasible operations resulted in the former increasing the energy savings by a very small amount relative to the loss of control. Also, the latter proved infeasible as no 2 columns could be coupled together. And that is all from us. On behalf of Neutral Plastics, thanks for watching.